This unit, we're going to do some more solving the systems of linear equations. Now, the only extension, though, is we're going to be doing inequalities. So meaning what we're going to be doing is we're going to actually combine the solving systems of linear equations from Foundations 10 with our inequalities that we had done in Math 9. This is also kind of split into two main parts. The first talk about just the systems of linear inequalities, so with the equations, well, not equations, but inequalities, and then we're going to talk about some optimization with it. And we'll see that coming into effect in section 2 and section 3. So getting right into it, we're going to do some graphing. So the first thing that we need to do is we need to remember how to actually graph a line. Now there's a few ways in order to graph a line. Easiest and best way is to put it into slope-intercept form. So y equals mx plus b form, where the m represents slope, which is rise over run, and b represents the y-intercept of the line. The second way that can be used, I know that I don't really encourage it too much because I focus a lot more on the slope-intercept, but it's to actually find out what your x and y intercepts are and then connect your dots. So our first example is we're going to do some graphing of this. So the first thing that we need to do is we need to convert it to slope-intercept form. In order to do that, we need to add a 2x to both sides. And then divide by the -5. So y would equal -2/5 x subtracting 2, which means our b value, our y-intercept, is going to be -2. And from that -2, we're going to have a rise or overrun of -2 over 5, which means we're going to be going down 2 and right 5. Down 2, right 5. Continue that on. Of course, we can also go up 2, left 5. Continuing on, and draw our line. I'll make sure I have blue. Of course, when we're drawing a line, can't forget that a line continues on forever, which means we need to put our arrows on. So there's our slope-intercept form. The other way is to determine our x and y intercepts. Now we're going to verify it by just using here. For example, we can see exactly where our y-intercept is and exactly where our x-intercept is. So we're going to prove that it is that. Remembering back to Foundations 10, in order to find out our x-intercepts and y-intercept, our x-intercept occurs when y equals 0. And likewise, our y-intercept occurs when x equals 0. So what does that mean? Well, in the context of our question, our -2x subtracting 5y equals 10. Wherever I see y, I'm just going to put 0 in. Of course, knowing that -5 multiplied by 0 is just going to be 0. So you don't really have it. So the short method of doing this is I can just divide by -2. Meaning when our y equals 0, our x equals -5. If we put that as a coordinate, it'd be -5, 0. And that's exactly what's proven here. Our y coordinate, sorry, not y, our x-intercept is -5, 0. To do the y-intercept, wherever I see x in this equation, I put 0. Subtract 5y equals 10. Of course, knowing that anything times 0 is just going to be 0, so we don't really have that, which means the next step is to just divide by the -5. I'm just going to go back and stick with the same colors. So y is -2. So when our y is -2, our x is 0, and that's going to be our y-intercept. So this would be a coordinate of 0, -2. And that's exactly what that is. That is the coordinate of 0, -2. So this is just another method. Of course, at the same time, this is what's done when we do it algebraically. So we're doing a nice reminder of how to do it algebraically that we had done in Foundations Pre-Calculus 10. Now with new stuff, we're going to get into some more linear inequalities. Now we've dealt with the inequalities in grade 9. We're just going to deal with a little bit more specifically. When I say specifically, I mean in the context of actually graphing. So the first thing that we need to talk about is a linear inequality is basically the definition. It's a relationship between two linear expressions in which one expression is greater than, less than, greater than and or equal to, or less than and or equal to the other expression. When linear inequalities are graphed, a few specific properties must be observed in relation to the type of line you use and where the possible solutions lie. So we had talked about some inequalities in grade 9. We had things like x being greater than and or equal to 9, or x being less than -7. Those were things that we had done as solutions. But in this case, we're going to actually be able to graph lines. And when we graph those lines, we have to pay attention to the specific properties. Greater than. Now, if you have a greater than sign in your equation, what's going to happen is that the line is going to be dashed, or another term for it is stippled. Because it's greater than, and we'll make more sense of this after we get into some examples, we would have to shade above the line. Less than, line is also dashed or stippled. The only difference, because if we're going to be shading less than, we need to shade below the line. Greater than or equal to, the line is going to be solid. Now, I'm just going to put that as quotation marks because we're going to talk about that a little more specific. But this one, because it's going to be greater than, we're going to shade above the line. And less than, once again, or sorry, less than and or equal to, we're going to have a solid line. Again, quotations. And shade below the line. Now these properties must make sense in the context of the question, as we'll explore some things in some subsequent questions. So when I say make sense, I'm talking about this solid or not. All right. So first things first, graph the following above problem. Actually, let's do a little quick reminder. Back in grade 9, and make a mention of it in Foundations 10, if we had something like x is less than -7, that means when we graphed it on a line, we had -7. Greater than -7 meant that we used an open circle. Sorry, this is sign less than, sorry. And then we shaded to the left because it's less than. Whereas when we had greater than, so if we use 9, greater than or equal to, we used a solid circle. Go off on that way. And this is the same kind of properties of what we're going to be talking about when we shade above or below. Obviously, on an x-axis, above would be to the right, whereas below would be to the left. If we're talking about vertically, so the y-axis, above would be above and below would be, or less than would be below it. So let's get into some actual graphing. So first one This is the exact same one that we've done before. So first things first, we want to add the 2x. Then we'd have a negative 5y equaling 2x add 10. Divide by the negative 5. Y would equal negative 2/5, x subtract 2. So this graph, go through negative 2, down 2, right 5, down 2, right 5, or up to left 5, up to left 5. And there's our line. So that's the equal to. We've done that. We've actually technically been doing it since grade, I know for sure grade 8, maybe a little bit earlier, but we usually graph them by a table of values and use that. Now we're going to get into some more specifics. We're still going to follow the exact same procedure. The only difference, though, it says that negative 2x subtracting 5y is greater than or equal to 10. So our first step is still going to be to add the 2x. We get a negative 5y is greater than or equal to 2x add 10. Divide by the negative 5. And one thing has to happen. As we had discussed in grade 9, there's something that's going to have to happen to this inequality symbol. Whenever you multiply or divide an inequality by a negative number, you have to switch the sign. Which means if this is a greater than or equal to symbol, it's going to switch to be the other direction. Less than or equal to. My favorite analogy for something like this is saying 1 is less than 100. We know that 1 is definitely less than 100. But if I were to multiply or divide both sides by negative 1, 1 divided by negative 1 is negative 1. 100 divided by negative 1 is negative 100. Well, I for sure am not going to want negative 100 degrees compared to negative 1 degree. Negative 1 is for sure a bigger number than negative 100. And this just helps illustrate the point that when you ever multiply or divide, because I could multiply by negative 1 as well. Same idea. Could be negative 2, anything really. If you multiply or divide by a negative number, the sign has to switch directions. So what that's going to do is now we're going to still graph. We still have a y-intercept of negative 2. Our ability to graph lines does not change. It still follows the exact same procedures. We get into slope-intercept form. We use our y-intercept and our slope to graph. But here's the difference. We're using this symbol, less than or equal to. Less than or equal to, we need to have a solid line, and we need to shade below the line. Now, I do keep that quotation marks, and I do reserve my right to use a quotation. Oh, sorry, should be solid line. For this case, and I'll show you different situations of where it's not going to be specifically the case. A little bit above, just fix that slightly. We have to shade below the line. This is a symbol for less than. So where would less than this line be? Well, it's going to have to be below it. And for our cases right here, this is all that we're going to need. I'll show you more later on in this section. If I do the same kind of work in this one, I still add the 2x, get a negative 5y is less than 2x add 10. divide by the -5. So because I've divided by a negative number, this symbol has to switch directions. Again, an inequality does not change our abilities to graph. It's just going to change a few specific properties as we do them. So now that we've laid out our outline, a greater than symbol means that we're going to have to use a dashed or a stippled line. And we have to shade above the line. So a dashed line is going to look like that. Of course, the line does continue on forever. And our shading greater than means above the line. And this is an example of above the line. I don't expect that your shading is absolutely perfect, but it does have to illustrate the point that you are in this section. Obviously, it would continue there. But the difference between this question and this question is that each of these points that are on the line are solutions. Whereas the points on this one are not solutions. And we'll go back to the symbols to help explain that. Less than and or equal to. Well, that means that all of our answers are going to have to be less than this line, as well as anything that is equal to this line. To be equal to this line means everything that it actually lies directly on this line. Whereas being greater than means it has to be above the line. But greater than does not mean anything that is exactly on the line. If you talk about speed limits, your limit is Trans-Canada is 110. It means that the maximum speed that you should be going is 110. If you go above that, you are very prone to getting tickets. So if you are less than, it means that this is your speed limit. You can go right at 110, but as soon as you go over that, it's likely that you could get a ticket. We won't go into all the specifics on the uncertainty on that, but that is the intention of the speed limit. And the exact same thing as inequalities with a line. Now in Foundations 20, we're going to work with primarily 3 different number systems. So the different number systems that we have been doing since grade 9, because we talked about the rational numbers, and in grade 10, we talk about other number systems, for example, the real numbers, fancy symbol being this one, the integers, which is a double bar Z. Oh, that's terrible. Or a double barred I, that's what I've seen. And the whole numbers, I usually add an extra line just to say that's that's actually the symbol for it. So real numbers are all possible numbers that actually make sense. So it means we can have decimals and anything like that. When I say makes sense, you can't really take the square root of a negative number, so those are numbers that are the ones that don't make sense. When we talk about the real numbers, we'll also talk about this R plus. Now it's a little distinction. It just means the positive real numbers. Which can also be used. Because there may be some times that you want to deal with positive numbers, but you can have decimals. The other two number systems talk about more discrete numbers that don't have decimals or fractions. The integers are only positive and negative numbers, whereas whole numbers are only positive numbers and zero. So obviously, positive and negative, you have zero in this as well, but a whole number just starts at zero and goes up with no decimals or fractions. Each of these number systems will affect either the type of line or the type of shading that is used, or even both. So let's do some graphing. Now here's a specific form. We're going to look at a few different things. This is the way that is written in your textbook, so we're going to use that. So first off, it is saying, okay, we have two variables. We have x's and y's in our equations. What we're going to be graphing, though, is this. These two things just identify the number system. So let's use the actual graph, or what we're going to be graphing, sorry. X subtract 2 is greater than 0. So to get the x by itself, we would add 2 to both sides. X is greater than 2. So how are we going to graph x is greater than 2? Well, that's not going to be a line. There's no slope. There's no y-intercept. But we've done them in grade 9 and grade 10. We kind of did them as well. Where is x? First off, where is x equal to 2? Well, it's equal to 2 right here, and right here, and right here, 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 all along this vertical line. Even the decimals, like every single point along this line is where x is equal to 2. So how are we going to graph this? Well, a few things. It says that we are greater than 2. So to be greater than 2 means that we're going to have to use, I want an actual line, use a dashed line. We're going to have to use a dashed line in this case. Because to be just greater than 2 means that we are not going to be equal to 2. Lines still continue on. Means any point that is on that line is not one of our solutions. But to shade greater than, well, the x's that are greater than 2 are all the ones that are to the right. The reason that I'm also shading everything here is because we're using all the real numbers. So the x's are real numbers, so every single number that makes sense means all decimals, everything, as well as the y values. That also makes sense. If there's a different restriction on these, then we'll deal with those ones. For example, here. Again, we're just saying that, okay, we have coordinates of x's and y's. Here's our inequality that we're going to have to graph. And then here's our number system that we're going to be dealing with. So we have negative 3y adding 6 is greater than or equal to negative 6 add y. We're going to have to get our y's to one side and our numbers without y to the other. So I'm going to subtract 6 from both sides, and I'm going to subtract y from both sides. Negative 3y subtract y is negative 4y greater than or equal to, and negative 6 subtract 6 is negative 12. Next step, divide by negative 4. Oh, I divided by a negative, meaning I need to switch my sign. So our y's are going to be greater than or equal to 3. So what that means is if our y's are greater, or sorry, y's less than or equal to 3, sorry. I must have said greater, I thought I did. Less than or equal to 3. That means our y value is 3. Now we have to also be very careful of how we're going to be doing this, because it says that our x's and our y's are an element of our integers. I know that your textbook uses I, but I like using z's because it's a number system that actually works for me. It basically means it's a Greek or Latin symbol for Zool, basically meaning kind of discrete numbers. Maybe a little bit, that may not be fully correct, but I know that Zool is the correct. I think that's the correct spelling. Anyways, okay, so integers. Integers means positive and negative numbers, but no decimals or fractions, which means the only ones that we can actually have here are anything that would be an intersection. We cannot put a value right there and say that that's part of our solution, because negative 5.6 is not an integer as an x. Same time, I cannot have a number right there and say that the point negative 5.6 positive 8.4. No, x's and y's are all the integers. We can't have those 2 points there. So the next part is because we're less than or equal to 3. Sorry, on the wrong spot. Less than or equal to 3 means we're going to have to go below there. Now you may start already looking at this and say, well, this is going to be a lot of putting dots in, especially since I have to use my pencil because I'm using a pencil in math. Well, as long as you've identified this, just use some arrows. It says, yes, I'm going to continue down. This area right here is my solutions. I'm perfectly fine with this, especially if we're dealing with a huge situation, a huge area like this. If it's a really small one, like if it was only these 3 spots up here, obviously you could fill that in. But this, a little bit too much. As long as you have this, the point is made. All right. This one looks eerily the same as this one, because they are. The only difference is the symbol. It's the inequality. This is a greater than or equal to symbol. This is just a greater than. So obviously we can fill in the same kind of work, and no matter what, it's going to come out the same. The only difference is that instead of using, because we would divide by the -4, instead of using a less than or equal to, it would just be a less than. So why is that different than what we had done just above? Well, it's for the simple fact that when y is less than 3, it means that any value that would be on that line of y equals 3 is not one of our solutions. So we would have to use a dashed line on there to indicate that, yeah, none of these values that are on that y equals 3 line are solutions. Whereas this one, all of these dots are solutions. Then to say that we are less than 3, well, we're going to have to, yeah, put our dots in. Try and be as careful as possible when you're doing assignments, as well as making sure that when you do your notes. But we can still say it continues down. It just cannot be on that line. So make sure it doesn't stay on that line. Alrighty. Because we had done word problems and we had converted word problems into equations in Foundations 10, we can do the exact same thing in Foundations 20. So a sports store has a net revenue of $100 on every pair of downhill skis sold, and $120 on every snowboard sold. The manager's goal is to have a net revenue of more than $600 a day from the sale of these two items, while combinations of ski and snowboard sales would meet or exceed this daily sales goal. We're going to choose two combinations that make sense and explain the choices. So let's get into it. We're going to make an equation for it. So it's saying that revenue is at least $100 for skis and $120 for snowboards. The goal, though, that they want is to have more than $600 a day. So if we're going to put this into an equation, every single ski will say, X for skis. So $100 for skis, adding $120 for snowboard. This revenue has to be more than $600 a day, which means greater than $600 a day. What combinations of ski and snowboard sales will meet or exceed this daily sales goal? Well, if we want to meet, that means that we have to be equal to as well. So I may have to just change the wording in here slightly, but you want to have more than or equal to. Yeah, let's just change that. Or equal to $600 a day. Well, here's our inequality. Let's get into the form of graphing. I'm going to have to add 100x. So 120y is greater than or equal to 100x. Add 600. Divide by 120. So y would be, because I divided by a positive, I do not have to change the sign. 100 over 120. Well, I know that 20 goes into both of them. 20 goes into 105 times, 20 goes into 126 times. So instead of writing 100 over 120, let's put it into something that's a lot nicer to graph. 5/6 x plus 600 divided by 120 is 5. So let's get into our graphing. It means that our y-intercept is going to be 5. And we have to use a slope of 5/6. Yep, there's already I knew that this started looking weird. Okay, you can't add 100, sorry, I'm so sorry. You can't add 100x and expect to get rid of your 100x's. You have to subtract it. I am so sorry. Either way, it doesn't change a lot of our work because we're just going to have this as a subtracting. Okay, now we're good. Okay, our slope, negative 5/6, which means we're going to be going down 5, right 6. Well, I can't really go down 5 again and right 6, so let's go here. Up 5, left 6. Now let's be careful. We have to make sense of what our variables are. Meaning, how many snowboard or how many skis can you sell? Oh, you can sell 1, you can sell 2, 3, you could sell 0. Can you sell negatives? If I were to just graph this without looking at the context of the question, here's what would happen. I would graph my line. So please don't draw this in. And greater than means all of this. Well, all of this means that we could sell -2 skis and 9 snowboards. This point right here, well, that says I can sell, what, 7.5 skis and 6.6 snowboards. That you can't do that. So let's look at the context of the question before we go too far. Our X's, our skis. Well, you can only sell whole numbers. You can only sell a whole number amount of skis. Same thing with our snowboards. We can't sell decimal values of skis or snowboards, and we can't sell negative amount of skis or snowboards. So when we do our graphing, apparently I got rid of my dots. We have to keep that in mind. We're going to have these dots. But because we have whole numbers, anything that might be on this line will not be part of our solution, which means we technically are not going to have a solid line. And that's what I mean by having a quotation solid line. So to sketch, absolutely, we can start off with it. We can draw a line, but we're not going to keep that because all of our solutions are going to have to be dotted in here. The only reason I have this line is to help identify different values that would actually be above that line. Now, would that be? That value should be above. So as I continue on in here, all of these values are the ones that I could have. Okay. Then I'm going to have to get rid of that line. Of course, it's selecting my arrow. All of these are the solutions. These are the ones that we are dealing with. Now we can choose two combinations that actually make sense. Have a revenue that is meeting or exceeding the $600 will be like that. I could have 2 skis and 6 snowboards. Why? Because for every single ski, it's $100. For every single snowboard that's sold, it's 120. 2 times 100 is 200. 6 times 120 is 720. We're at $920. That is absolutely a good revenue if you want to have a minimum of 600. Another one will be like right there. I could have 8 skis. 8 skis, there we go, and 0 snowboards. Using the exact same rationale. Every single ski is $100. Every single snowboard is 120. Well, 0 times 120 is 0. 8 times 100 is 800. And there we go. Absolutely, if you want to, you can continue all of these dots. You can fill this entire thing in. I'm fine with the arrow. I'm just going to have some quick fun here. With a pencil, it can be more time consuming. And I would not encourage highlighters for this purpose because highlighters are going to make this entire graph look messy, as well as it's going to become more difficult in our other sections. Now that we've made sense of what our choices are, you can go have some fun.